Okay, so we'll start with 2D flows. So what you will have 2D flows? So you will have two things like you will have an X term and a Y term, right? So say like we'll start with X dot equals to say some f of x comma y, and some y dot you will have some g of x comma y, right? So these are the two systems, coupled systems, right? So what is this x dot all about? This x dot is nothing but dx by dt. Okay, this is nothing but dx by dt, rate of change of x. Now we have moved to continuous time domain, right? We are no longer in the discrete time. We have come to continuous time domain, right? So this is the 2D flow. So 2D flows. So basically, what is the scenario? You have x and y. You have x and y, and you have any for any point x comma y, you have a vector that is pointing to x dot and y dot. Okay. For any x comma y, you have a derivative for each of these variables x and y, saying how these variables change with respect to time, and this is how represented by a vector x dot and y dot. Okay. Fine. And for this equation, how what is the solution? That's the question. So of course the solutions are xt and yt, right? The solution of any system is like what is xt and yt. I mean how x and y change with respect to time, right? So how to know whether the solutions will exist? That's the question. How to know if the solutions will exist? Now the solutions exist if these vector fields you have over here are continuously differentiable. Okay, that's I think you have been learning since class 11th. You have been learning since class 11th that if these guys are continuously differentiable, okay, so these are continuously differentiable, right? If this is a continuously differentiable vector field, then solution, that is xt and yt, exist and are unique, right? They exist and are unique for any initial conditions. For any initial conditions, right? You understood this, right? So for example, this system, you start with any initial condition x naught and y naught. Any initial condition doesn't matter. My means these are various types of initial condition, doesn't matter, till your the right hand sides f and g are continuously differentiable. The solutions to this flow will always be unique. I mean the flow can be like this, but eventually they will point to the same solution. Okay, so this is one of the most important theorems on existence and uniqueness. I hope you remember this. Those who have taken like math in their class 11th should already know about this, right? Existence uniqueness theorem. Like if f of x comma y and g of x comma y are continuously differentiable, then no matter what, whichever initial condition you start with, the solution will be unique. What does it mean, the solution to be unique? Their fate will be the same. I mean, if they start from whichever initial condition, the long-term behavior will be the same. Okay. Fine. So how here the trajectory is? So you know in 1D flows, those who are present in last class, in 1D flows, you will not have oscillations. Okay, 1D flows never have oscillations because 1D flows only have one variable x, and they will have only positive and negative values, the room to move, right? They will only have a number line, that is 0, only positive and negative. They can move either here or here. They cannot move here and again come back here. That cannot happen. Why? Because if they go here, they should be going here only, this side only. They cannot come back, because if they come back, they are intersecting these points again, and that intersection can never happen. Similarly, this here also, here rather it has more room to move. In 2D systems, you have more room to move, right? How you have more room to move? You have x and y, and the vector field is like you can have these solutions. These are the solutions it can have. Now this solution can be a good solution. However, this solution can never happen. This can never happen. Why? Because this you started from x naught y naught. This is the initial condition, and your points are moving like this, right? But at this point of intersection, say this point of intersection, let us zoom. You can see that there are two possible future trajectories. There are two possible future trajectories, right? There are two possible future trajectories. Okay, there are two possible future trajectories means, is it possible? If you are at one point, can you have two future outcomes? You can never have. You can never have two future outcomes. Like if I am here, I can either travel at one point of time, I can travel only in one direction. I cannot travel at one point of time in two directions. Okay, so that's the idea. So therefore, in 2D space, they cannot intersect each other. Neither in 3D space. Okay, neither in 3D space also they cannot intersect each other. Fine. So this is one of the important points. Okay, so therefore, whatever chaotic attractors and all those things you are seeing, they are having such a nice geometry because they are not allowed to intersect. They are not allowed to intersect. So whenever they are nearing to one curve, they are forced to bend. So they bend and go nearby. Okay. So those who have seen and worked with Lorentz systems, you might have seen that they have very nice looking butterfly shape. Okay. And those butterfly shapes, they don't intersect. They don't intersect. So to understand it, you can visualize, you can rotate and see that it will be very close to each other, but they never intersect. Okay. Anyway, so these are the ideas. And yes, due to this, you can see that due to this behavior, uh, you can see that in 2D systems, you can have existence of periodic orbits. You can have existence of periodic orbits. Periodic orbits. Like many of you already pointed out. Okay. Many of you already pointed out that say suppose you have this region, right? Now this is a periodic orbit. Why? Because it started from one point and it came back to one point. So this is a periodic orbit in continuous system, right? Now why it is a periodic orbit and how it is formed, that's the question. Because if you start from any initial condition inside this curve, then it has only one possibility, that it can only approach this curve. Can it have any other possibility? Can it stay at that point at fixed? No, it cannot stay, because there is already a stable periodic orbit on the outside. So inside cannot be a stable fixed point or equilibrium point. Can it go outside? It cannot go outside. I mean, can it go like this? Can it go like this? It cannot go like this. Why it cannot go like this? Because if it goes like this, there will be an intersection here. There will be an intersection here, right? Do you agree or not? Yes, there will be intersection, right? So it cannot go outside of the curve. So it has to stay inside only. Similarly, can any point which is in the outside come inside? So any point outside you started, then it started going like this. Can it go like this inside? No, it cannot happen. Why? Because at this point, it will again have two directions. It will again have two directions, right? So what it can do, if you start from something outside, it can like travel like this. It can travel like this, but at least approach and become one of them. And become one of them. Are you getting the idea? So it can become one of them, right? So it can never cross. Is it this clear or not clear? Is this clear? How many clear? Clear, clear. Okay, not clear, not clear. Okay. So we'll start again. So you understood that they cannot intersect. You understood they cannot intersect. Suppose this is that periodic orbit. Why it is a periodic orbit? In discrete maps, you had discrete points like this, right? You say you started from one point, go apply the map F, apply the map F. If you apply the map F, you come back to the same. Wow. You come back to the same point again. I think I have to draw in a separate one. Yeah. Let's redraw. Anyway, we can draw it here. So you have this structure, right? You have this structure over here, right? It's behaving a bit weirdly, right? It is. Okay. So this is a periodic orbit. Why? This is a periodic orbit. This is a periodic orbit. A periodic orbit. Now, why this is a periodic orbit? Because you started from one initial condition, that is x naught, y naught, and you progressed with time. It went on continuously, and it came back to the same point again. It came back to the same point again. So this is a periodic orbit, right? Now my question to you is, this is in the 2D space. This is in the 2D space. That means x and y. Now what I am suggesting is you can start here inside any point also. You can start initial condition any point here also, right? Now if you started from here, what fate it has, means what are the possible options it can do dynamically. It has to move dynamically, right? It has to evolve, right? Now can it stay at that point? That cannot happen, because periodic orbit is on the outside. That is the stable attractor there. So it cannot happen. So it has to evolve. It has to evolve. Now if it evolves, so it has to go like this. Can it intersect? It cannot intersect, right? So this thing cannot happen. This thing cannot happen. Can it go like this? Yes, till now it is good. Now it is good. But can it go like this? It cannot go like this. Why? Because at this point of intersection, you will have two possible futures, which is not possible, right? So therefore that cannot happen. Therefore that cannot happen. Now what other possibility it has? If those things cannot happen, what other possibility it has? It has something like this. It can keep on wandering. It can keep on wandering, right? But it can keep on wandering but not touch each other. But not touch. Okay, I mean, yeah. Okay, it cannot touch. Okay, that's the idea. Okay, so if it cannot touch, what are the options? So if you continuously evolve, it will become one of them. It will slowly converge to this orbit. It will slowly converge to this orbit, right? Do you agree? Do you agree? Right? Now, this is the case of any outside orbit. This is the case of outside orbit. Can you start from anywhere outside? X naught, Y naught? If you start from anywhere outside, can it happen something like this? Can it happen something like this? No, it cannot happen. Why? Because at this point, it has this direction and this direction as possible features. So therefore, this cannot happen. This cannot happen. Right? What else can happen? What else can happen? You started from initial condition here, right? What else can happen? It can keep on wandering. It can keep on wandering, right? It can keep on wandering. Gone, gone. How it will be? I mean, it can do any sort of things you like to do, okay? But yeah, slowly it will become one of it. Slowly it will become one of them, right? It cannot be inside. I hope you understood this concept. So this is the idea. So due to this behavior in 2D systems, that they cannot cross each other, due to this behavior, periodic orbits are formed. Okay, due to this behavior, periodic orbits are formed. Why? Outside orbit are cannot go inside. Inside orbit cannot go outside. Inside orbit cannot go outside. Okay, outside orbit cannot come inside. Inside orbit cannot go outside. So what is the possible future? It can only form a periodic set. Okay, periodic set where things will keep on repeating. Where things will keep on repeating. Okay, so this is the idea in 2D systems. So therefore, in 1D systems, you cannot have periodic orbits. You cannot have oscillations, right? That we discussed in last class. Whereas in 2D systems, you can have periodic orbits and oscillations. Okay, this is the reason why 2D systems, 2D dynamical systems can show oscillations due to the fact that they cannot cross each other. Very fundamental property leading to that birth of oscillations can take place. Very, very fundamental idea. Okay, very fundamental idea, right? So in simple harmonic motion in your class 12th physics or 11th physics or BSc, I hope you have read simple harmonic motion, isn't it? How many of you read simple harmonic? Yes, everyone has read simple harmonic. And in simple harmonic motion, you might have drawn many trajectories, right? Periodic systems, periodic orbits. So how the first thing you should have asked, how high periodic orbits are formed, first of all? Because it's the only reason is because the trajectories cannot cross each other. So inside things cannot go out, outside things cannot come in. So therefore, it's a periodic structure, right? I think you can think of this. This you do regularly. This you do regularly, right? Your home. This is your house, right? If in your house, this is your bed. Okay, suppose this is your bed, right? So you start from the bed, go to the TV room, right? You go to the kitchen, right? You go to the garden, and finally you come back to the bed only. Okay, right? So this is periodic orbit. Okay. Anyway, fine. So now the idea is like in 2D systems, how we can analyze these 2D systems. As you will see, the 2D systems are very rich. We'll see one example after another how 2D systems are very rich. Okay. Uh, for that, you have to know about two things. That is, suppose you will start with linear 2D systems. That's the simplest case we can start. Okay, linear 2D systems. Okay, so in 2D systems, you will see many things like this. Like this is a equilibrium point, and the equilibrium point will be so nice that you will see the flows will be flowing like this. Okay, the flows will be flowing like this. Okay, right? It's a very interesting flow. So you will see some trajectories like this, and we will understand when this will happen. We will understand when this will happen. I hope if this you see what it reminds you, what it reminds you, something it should remind you. How many of you sat on a horse? Horse. So horse saddle, have you known? Horse saddle. So on one side it will be very nice, on other side it will be like this, right? On one side it will be like this, on other side it will be like this, right? It's a horse saddle, right? So in one point you will see this it is going like this, and other point it is going other way around. So it's a saddle kind of thing, okay? So that we'll see, don't worry. And there are many different approaches which you can observe. Uh, I have not drawn here, is it? Okay, okay. Okay, we'll start with linear 2D systems. What is linear 2D systems? Linear 2D systems are of the form x dot is ax, where x is just xy, and the capital A is just some matrix A, B, C, D. Okay. So what does x dot equal to ax looks like? How it looks like? Anyone? X dot y dot equals to, yes, isn't it? Is it linear? Yes, it is linear. Why? Because you have x and y terms. Because you have x and y terms, no? Therefore, it is linear. Agree. Okay. Our job is to understand the behavior of these systems. Our job is to understand the behavior of linear systems first. That's the simplest thing to take ahead. Okay. Now to do this, you can say what is the equilibrium point? What is the equilibrium point of linear systems? Yes. What are the equilibrium points? What are the equilibrium points? Anyone? What you do? You set. So what is the equilibrium? I mean a trivial equilibrium point. Trivial. Yes, a trivial equilibrium point is zero. Why? Because these are straight lines and you are setting to zero. And these straight lines will always pass through origin, right? So you can see equilibrium point is 0, 0 is the trivial one, is the trivial equilibrium point. So this is one of the trivial equilibrium points, right? Agree? Now, when this equilibrium point is stable and when it is unstable, that's the idea. That's the idea. Okay, that's the idea. Fine. Okay. So here in this 1D flows or 2D flows, we say an equilibrium point is stable. An equilibrium point is stable if all eigenvalues if all eigenvalues have real part less than 0. Okay. An equilibrium point is stable if all real part of the eigenvalues are less than 0. Okay. Otherwise, unstable. Fine. Agree. Okay. So for that, what we do is how to find solution to this. How to find solution to this 2D system. That is the idea. So this is a 2D system. So definitely, and this is a vector, right? It will be in a 2D space. It is like a vector. So how this vector will be going? So one fundamental tool is definitely eigenvalue and eigenvector will be in the picture. Definitely eigenvalue and eigenvector will be in the picture, right? So therefore we assume this is somewhere many you don't like, but this I assume that the solutions are of this form. That is x vector is equal to something like, say, your vector v e to the power lambda t. So this is just a small derivation we are doing just to show that eigenvalue and eigenvectors are responsible for the stability. Eigenvalues and eigenvectors are responsible for the stability, right? So how can you understand stability here? Stability depends on the eigenvalue and eigenvectors. Okay. So just take this thing here. So what is Ax then? Ax will be nothing but A lambda e to the power Vt. Is it? Okay. Okay. So how can we solve this? I am asking you. How can we solve this? What is x dot? If x is v lambda e to the power Vt, what is x dot? What is x dot? Tell. What you will get? Hmm? So x dot equal to lambda v e to the power lambda t, right? So can I write x dot equals to ax now? What is x dot? Lambda v e to the power lambda t. What is ax? Av e to the power lambda t. So what you got? Av equals to lambda v. Av equals to lambda v, right? So nothing else. So this x dot equals to ax. This problem, okay, has transferred to simple eigenvalue problem, isn't it? This problem has simply transferred to the eigenvalue problem. Av equals to lambda v, right? Now what should we do? What can we do now? What's the next step? So how can we get lambda? That's the idea. Your job is to, what is your job? What is your goal? What is your goal? Your goal is to find lambda and v. Why? If you find lambda and v, it can give you what is x. Because x is nothing but v e to the power lambda t. If you get this quantity and this quantity, you can find what is the behavior. You can predict the behavior of the system over a long time interval, isn't it? As a dynamical system, what we are doing in this 2D flow, we are trying to understand what is the long time behavior of the dynamical system. What is the long term behavior of x and y as time tends to infinity, as time increases, right? So, what's the idea now? Yes, the idea is to find v and lambda. The idea is to find v and lambda, right? Yes. Okay. How will you find v and lambda? From this equation, av equals to lambda v. Av equals to lambda v, right? How can we find lambda? Tell me how we can find lambda. How to find lambda? How to find lambda? Hmm. How to find lambda? Hmm. How to find lambda? What shall you do? Do you remember about characteristic equation? Just set this to 0. Determinant of a minus lambda to 0, right? If you set to 0, you will get lambda. What is lambda, right? After you get lambda, can you find v? Yes, a bar equal to lambda v bar. Yes, you can find. So you will get both the eigenvalue and eigenvector, which will give you the solution to the differential equation, right? Understood? So you can predict the trajectories of the system. Now, before that, I want to tell that for any matrix A, this is a note. This is a note. For any matrix, any square matrix A, okay, what is how determinant and eigenvalues are related? Determinant of A is equal to product of eigenvalues, isn't it? Determinant is equal to product of eigenvalues. What is the trace of A? Trace of A is nothing but sum of eigenvalues. I hope you know trace, right? Do you know about trace? What is trace? What is trace? Suppose A equals to 2, 3, 4, 5, right? What is the trace? Trace is nothing but this diagonal, you have to sum it. Okay, what is the sum? 2 plus 5. So trace of A is nothing but 2 plus 5, that is 7. Okay, what is the determinant of A? 2 times 5 minus 3 times 4. That is minus 2. Okay, done. Okay, fine. So this is the idea. So fine. So now let us see some examples so that you can appreciate what is going on. Okay. And then we can classify some more things here. Okay. So let us look into something like this equation. X dot equals to say 2x and y dot equals to say minus 3y. This is a 2D flow, isn't it? Is this a 2D flow? This is a 2D flow. Alright, why? Because it's a 2D linear flow. If I want to be specific, this is a 2D linear flow. Now my question to you is, can we analyze? Our job is something like this. Can we analyze? Can we analyze on x and y? How this x and y keep on varying? That is our job. Can we analyze how x and y keep on varying? What are the solution and how they behave? Right? Is this linear first of all? Yes, they are linear. Right? They are not coupled. They are not coupled. X depends on x, y depends on y. X doesn't depend on y doesn't depend on x. This is the simplest system we can do. Okay. Now, can you tell me what is the solution? What is the solution of x? Can you solve this equation? Yes, you can. How? Yes. Take integration. What will we get? 1 by 2. Yes. Plus some constant. Okay. So what you got here, ln x is nothing but some 2 times ln t plus c dot, right? So what is x? Hmm? Sorry, this should be t, right? This should be t, no? Okay. What should be? X equals to e to the power 2t. Some constant c naught or c, constant c e to the power 2t, right? Do you agree? Yes. So what should be similarly for y? For y should be what? So similarly, what you can do? Dy by, mhm, isn't it? So dy by y equals to minus 3 dt, right? So ln y equals to minus 3t plus c. Okay. So what you get? Y equals to some constant t e to the minus 3t, right? Got the idea? Hmm? Happy. Okay. So what shall we do next? What shall we do next? How they should look like? So I gave you how x varies with time. They vary like something like e to the power 2t, and y also vary with time as something like d e to the power minus 3t. So this I gave you two ideas how they will behave. How they will behave. Can you plot the solutions here? That's my question to you. How can you plot the solutions? Hmm? Can you plot the solution? These are the solution, right? Agree? Does this flow have a equilibrium point? Does this flow have a equilibrium point? Yes. How will you find equilibrium point? Equilibrium point. Set x dot equal to 0, y dot equal to 0. What you get? X equal to 0 and y equal to 0. So the origin is a equilibrium point. The origin is an equilibrium point, right? Origin is an equilibrium point, right? Okay, fine. Now, is the equilibrium point stable or unstable? I gave you a behavior, right, before. You can find the matrix, right? Can you write x dot equals to ax? So x dot equals to ax. Then what is a here? 2, 0, 0 minus 3. Agree? 2, 0, 0 minus 3. What are the eigenvalues? What are the eigenvalues of this matrix? 2 and minus 3. Because it's a diagonal matrix, right? So the diagonals just values will be the eigenvalues. So one is 2, one is minus 3. One eigenvalue is 2, another is minus 3. So yes, it won't be stable because one of the eigenvalue is positive. One of the eigenvalue is positive. So it is not stable, right? So what will happen? It is mixed nature. One eigenvalue is unstable and another eigenvalue is stable, right? So it will have mixed nature of stable and unstable together. So how it will be looking in our phase space? That's my question to you. How they will be looking? Okay, fine. So these are the two eigenvalues. Okay, what can be the eigenvectors? What can be the eigenvectors here? Hmm? AV equals to lambda V, right? So 2, 0, 0 minus 3, V1, V2 maybe is equal to what? Maybe for 2, lambda equal to 2, let us find. For lambda equal to 2. So what's the solution? Can you get solutions here? Ax equal to lambda x. 1, 0. Is it? What's the idea? Okay. Okay, I want everyone to use their visualization power to visualize this, the solutions to this. Okay, fine. Let us use these two things here. X equals to c e to the power minus t and y equals to this. By using these two, can we predict how it will look on the figure on the right? Can you see this x here? Can you tell me, as time increases, where x is going? As time increases, x will be going exponentially. X is growing exponentially and will be going towards infinity, right? Because e to the power 2t is there. As time is positive, as time is keeping on increasing, x will go on to infinity, right? Agree? Now, when x is going to infinity, we understood as t tends to infinity, right? This is one factor we understood from this equation. Now from the second equation here, can you tell me, like as time goes to infinity, where y is going? No, y is going to 0. Yes, y is going to 0 as time is going to infinity. Do you agree? Why? Because it's exponential minus 3t. It will keep on exponentially decreasing to 0. Right? Agree? Right? Now can you combine these two together? Now as time increases, what is happening? X is going to infinity and y is going to 0. X is going to infinity and y is going to 0. Can we do this here? X is going to infinity. Okay, x is going to infinity, y is going to 0. Right? How it should look like? Y is going to 0 means the vector should point in this direction, isn't it? Okay. If, yeah. So, yeah. So y is going to 0, right? Agree? Now x is going to infinity. So how it should look like? X is going to infinity this side, right? Agree? X is going to infinity means on that side, suppose. It's keep on increasing, right? So the resultant of these two should be in this side, right? Agree? Right? So how it should look like this figure? I'm giving you a visual intuition. So how it should look like? Does it look like this? Do you agree to this? Yes, why? Because if you go along this direction, along each of this direction, y is exponentially decreasing, whereas x is exponentially increasing and moving towards infinity. But at the same time, y is converging to 0, right? Do you agree? Fine. Okay. Now this is, I have taken a simplest case. This I took a simplest case, that positive x-axis, right? Positive x-axis. Now can you think of these axes? If you think about this axis, it will look like this. It will look like this. Okay, it will exactly look like this. Fine. You can see here the points are going like this. Here the points are going like this. So here y is decreasing. Y is decreasing, whereas x is increasing. Fine. Any issues so far? Here also on this side, on the second quadrant, the y is decreasing. You can see whenever the point is coming here, it is traversing this side. The y keeps on decreasing and x is keeping on increasing and going towards minus infinity. Right? Same is happening on this side. Same is happening on this side. Okay. Y is again coming to 0, coming towards 0, and x is going towards infinity. Same on this quadrant also. Right? Agree? I hope that is okay. Fine. And as some of you already told, that one eigenvector is 1 0 and 0 1, right? So you can see this is the equilibrium point over here, the green point. That is the origin. That is an equilibrium point. And you can see that the eigenvector, if you compute, one eigenvector will be approaching towards the equilibrium point, another eigenvector will be going outside of the equilibrium point. So it has a mixed nature, right? One is stable direction, another is unstable direction. Agree? That's what we saw in this calculation. That's what we saw in this calculation. One was positive, one was negative. One is stable, one is unstable. Right? Agree to this, no? Fine? Hmm? Now, now this is the idea, like we'll be considering different examples, and in different examples, my role is to show you different dynamical behavior in this system. Okay, that's what we will be doing. Okay, so that one, the first one was the easier one. The first one was the easier one. So let us go to the second one where you see something like coupled system. So you have this system. Suppose this is a coupled system. Is it? Agree? Is this a coupled system? Yes, because the rate of change of x depends on x and y. The rate of change of y depends on x and y. Right? So therefore, it's a coupled system. Now your job is to understand how the values of x and y change in this plane, xy plane. That's the idea. How the vector field looks like. Same as in the previous figure, you understood how if you started from here, these are the initial conditions. Mind you, these are the initial conditions. These yellow points are the initial conditions. This is where you start your journey, right? This is where you start your journey from. Each of them are initial conditions. Okay. Now my question to you here is, for this system, how the vector field will look like, and guarantee that it will look different from the previous case or same as the previous case. That's my question. Okay. So what is can you reframe it? Can you reframe it in terms of x dot equal to ax? If so, what is a? Can you write this? X is xy. So can you write like this? X dot y dot is nothing but -4 -3 2 3 xy. Can you write in this term? Yes, you can write. So this you can say this is x dot and this is a, this is x, right? So we understood that the solution x vector is nothing but v e to the power lambda t, right? That was our solution, right? So therefore, my question to you is, therefore we have to find the eigenvalue and eigenvector of of a, right? So if you have a is this, what is the eigenvalue and eigenvector? Find eigenvalue and eigenvector of this. Lambda 1, lambda 2, v1, v2. Yes. Okay, so far what you have understood is what is lambda 1? So lambda 1 is equal to 2 and the lambda 2 is equal to -3, right? Now corresponding to the eigenvalue lambda 1, what is v1? You will get 1 minus 2. And what is corresponding to v2? You will get 3 minus 1. Okay. Or any multiple of this is also correct. Any multiple of this vector is also correct. Any multiple. Okay. If your eigenvector is any multiple of this, it is correct. Okay. You want to compute again the eigenvalue, eigenvector here. Eigenvectors, why is the problem? A v1, a v1 equals to lambda v1, right? So what we are getting, for which one we will try? -4, -3, 2, 3. V1, v2 suppose. Okay. Or yeah, equals to lambda that is it correct? Can we solve these two equations? What are you getting? If you solve this equation, there are two linear equations, just two simultaneous linear equations. So -4 v1 -3 v2 equals to 2 v1. So what we are getting? -6 v1 is equal to 3 v2. To cancel, -2 v1 equals to v2, right? So what you got? v2 equals to -2 v1. So if a vector is v1 v2, that is being given by v1 and -2 v1. You can take v1 to be common, 1 minus 2. So any multiple of 1 minus 2 is still an eigenvector, right? So therefore you can get 1 minus 2 as an eigenvector. Okay. Similarly, you can do the other eigenvalue. Fine. Now let us see. Okay. Now let us see how these things are in the space. Now you tell me lambda 1 equals to 2 and lambda 2 equals to 3, right? So lambda 1 equals to 2. The real part is greater than 0. So this is the unstable eigenvalue. Unstable eigenvalue. So that means the V1 corresponding V1 1 minus 2 is the unstable eigendirection. Unstable eigenvector. Yes. So that direction will be unstable. That means points will go outside of it. Points will move outside of the means far away from that equilibrium point. Right? Agree? Now lambda equals to minus 3 is the stable equilibrium, stable eigenvalue, right? Is the stable eigenvalue. And V2 corresponding to lambda 2 is equals to 3 minus 1. That's the stable eigendirection, stable eigenvector. That's the stable eigenvector, right? So this is the whole story you have captured in this part. This is the whole story, right? Now my question is, what is the equilibrium point of the system? Of course, origin. Of course, origin is the equilibrium point, right? How? Set x dot equal to 0. Set x dot equal to 0, y dot equal to 0. The one of the solution is 0, 0. One of the solution is 0, 0, right? So therefore, you see this is the equilibrium point. Origin is an equilibrium point. Now my question to you is, can you draw the eigenvectors? Can you draw the two eigenvectors in this plot? Okay, one is what? 1 minus 2, right? 1 minus 2. So x will be 1, x will be 1 and y will be minus 2. Fine. So it will be this point, right? Okay. Now let's plot the second eigenvector. Second eigenvector, that is 3 minus 1. X equal to 3, y equal to minus 1. Where it will be? X equal to 3, that means very further away, right? And y equal to minus 1 means here somewhere. So it will be something like this here, right? Agree? Agree to this? Agree? Fine. So let us draw two of this set. Fine. So 1 minus 2, 1 minus 2, any multiple of that, what will happen to that vector? It will be on that vector itself, right? So it will be a vector like this. Isn't it? It will be a vector like this. Agree to this. No? Is this a, so this is V1, this is V1. Red is V1, 1 minus 2. 1 minus 2. Any multiple of that is also an eigenvector. So it will lie on that vector. So that's how you created that line. Fine. I hope everyone agrees to this. Okay. Now, is this a stable eigenvector or unstable eigenvector? Stable or unstable? Unstable. Already we deduced. Already we deduced. So what will happen to this unstable? The points will move away from each other. The points will go away from the equilibrium point. The points will go away from the equilibrium point. That is unstable, right? It is unstable eigenvector. Unstable. Unstable direction. So therefore, points will move further away from the equilibrium point. Agree? Fine. Now let us come back to the stable eigenvector direction. That is a bit difficult to draw, but I can try. Like it should pass through the origin, right? It should pass through the origin. So how it should look? Okay, still not correct. Yeah, kind of correct. Yes. So this is a stable direction. This is a stable eigendirection. Why? Because this eigenvector is V2 and it is stable eigendirection. Stable eigendirection means the trajectory will come closer to the equilibrium point. So therefore they will point towards the equilibrium point, right? They will come close to the equilibrium point. Can you see they are coming close to the point here? Equilibrium point, whereas this guy is moving out. This guy is moving out of the equilibrium point. Fine. Agree to this dynamics? This is the story of eigenvalue, eigenvector, nothing else so far. Visualization. Agree? Any problem with the understanding? Any problems? No. Fine. Okay. Now my question is, how now any point which will lie on the eigenvector, we know they will go out, they will come in. But what will happen to say this point? Suppose we started from this point. We started from this point. What will happen to that point I am asking you? Of course, this point when it goes like this, it will be carried forward because this guy is moving in this direction. So they will move in this direction, right? They will move in this direction. The moment it comes closer, it will feel the heat of this guy moving out again, right? So what will happen? This guy will turn like this, right? It will turn like this. Agree? Yes. So what will happen similarly to point here? Suppose you are starting from here. Suppose you are starting from here, what will happen? Since you are starting from here, these directions are going inside. So you are going like this. Okay. The moment you come here, it is closer to this unstable direction, it will push you away. So it will go like this and follow this trajectory again. So it will go like this, come back in this direction. Right? Fine, no? Fine. So similarly, you will be seeing something like this. Like it will go like this, come back like this. Similarly here, go like this, come back like this. Here. Okay. Now what will happen here? Suppose you start from here. You start from any point, say here. Any point here, what will happen? Yes, this is the stable direction, so it will keep on going, and then yes, again, this guy is also going outside, so it is keep on going like this. Yes, fine, understood. Hmm? No, no, yeah, understood. Okay, so what will happen to this point also? This point also will go like this, right? So similarly, what will happen to say this guy? What will happen to say something like this here? So since this guy is coming towards the origin, this guy will force this guy to come to the origin, and still it will go like this, right? Because of this unstable directions here. And similarly, your corresponding trajectories will also follow similar route, right? So can you see the diagram here, how complicated this diagram is, but just by eigenvector and eigenvalue, you have drawn this phase portrait and you have shown how the points move throughout the space, bounded by the unstable eigenvector and the stable eigenvectors, right? So you can see some points are coming closer in some direction, some points are going away in some directions. There is a mixed property. It's a mixed property. Some are coming towards, some are going outside, some are going away. So it's a mixed property. Such a mixed property, it's a mixed property, like some coming closer, some coming closer, some going out. Okay. This property like coming closer and in the some direction going out is known as saddle property. Okay. So therefore, this equilibrium point is a saddle equilibrium point. Okay. This equilibrium point is referred to as a saddle equilibrium point. Fine. Okay. Hmm? Okay. So see, this behavior is exactly same as like this behavior, isn't it? This behavior is same as this behavior, isn't it? Why? Because you can see it is going like this, it is going like this. Some are coming closer, some are going away, right? So you can see similar kind of behavior here also. Fine. Okay. Now, any other possible behavior can exist? My question is to you. Can any other possible behavior exist? What you can think of? What other behaviors can exist? Hmm? Okay, so let's go back to the next one. So what happens? What happens if you take a different dynamical system, that is x dot is say 3x plus y and y dot equals to say my 3y. Okay. If you have this system, can you say I can write it in this way, right? x dot y dot is equal to 3 1 0 3, right? xy. So you can say this is x dot equals to say ax. Fine. So what is A matrix here? 3 1 0 3, right? So what are the eigenvalues here? What are the eigenvalues for this one? What are the eigenvalues and what are the eigenvectors?